When talking about numbers, you have several flavors to choose from. But what makes irrational numbers so special? And what makes this diagram so wrong? Rational numbers, including repeating decimals, are integer ratios. Irrational numbers are not. Let's draw them with a point and a distance and an angular velocity. Then we will circle back to do it again with twice the angular speed, half the time, or 2 cycles for the price of one. Now the fun part, putting them together to trace out a shape called an encycloid. This one is called a cardioid or cardioid or something because it kind of looks like a heart maybe, but names are not important. None of this is important. It's just fun unless you're a square. And what about this ratio? It will take longer to reconnect. Other shapes will take even longer, but irrational numbers never reconnect. They never meet, never, ever, not in a million billion years. The entire circle will turn white, but not every point will be white because the 2 points will never reconnect where they started. This is phi, by the way. It's called the golden ratio, and there is its equation. And here's a fraction that comes close, but no ratio can be right. Turns out the golden ratio is a contradiction in terms because it's not a ratio, it's an irrational number. And speaking of contradictions, I have a problem with this picture. If rational numbers are this and irrational numbers aren't, well then what goes here? We do. And yes, we are still irrational because we are outside of the rational club, but we are transcendental, meaning not algebraic, not the root of any polynomial. More rearranging, these are constructible, with tools, but cubed roots are not. And now we review. Rational numbers are ratios. Phi is not, but it is algebraic, hence the equation. It is even constructible. The square root of 5 is constructible. The cube root of 2, however, is not constructible. It is, however, algebraic. And pi and e are transcendental. These series, like the epicycloids, would go on forever. And each region is like a playground, an infinitely big playground, and yet there is always something more to discover. Infinitely many, as it turns out, does not mean all, and that is the paradox of irrational numbers.